go. Hello and welcome back to Calculus 2, section 7.2 on exponential models. So we're going to go back to our pre-calculus days and work out on basic pre-calculus exponential models, and then we're going to add calculus on top of it in terms of limits, derivatives, and integrals, and see what those calculate, what those give us once we are done with the model. So mathematical model is just a formula that describes something that is in a world around us. So the exponential models have two flavors. We said that there is the growth flavor going through this value a. So this would be y equals a e to the kt. T is the time input variable, is in time, and now depending on what you guys have, could be minutes, could be hours, could be days, could be years, right? Depends on, mainly it's years, but could be anything. So that's the, and we call this one growth. And we want to talk about either population or money. Now, on the other side of the wall, we're going to have the decay model. As the time goes, the amount of stuff A diminishes in time. So y equals a e to the kt. K is negative in this case. This is called exponential decay, and we want to talk about mass decay, radioactive decay, garbage decay, metabolizing drug in a system. There are a whole bunch of things that we can talk about with the decay. Now, so for the growth, k is larger than 0. When k is positive, the values grow. When k is negative, they diminish. So on the growth side, population, if unchecked, grows exponentially. We have seen that anytime when we thought we were smarter than nature and then eliminate some kind of species that we found to be not likable or pesky, and then whatever else that was much worse flourished. There are some examples where there was an island somewhere where people decided they didn't like cats, and they went around that island and they killed all the cats. And at that point, the mice and rabbits multiplied to that point that they destroyed an entire vegetation of the island, and pretty much almost, because they didn't like cats because they were eating the eggs of some birds, special birds that were nesting on that island, and they decided, well, kill the cats. As soon as they killed the cats, the population of rabbits and mice and rats went to the point where the rats ate the eggs and the rabbits and everything else ate the rest of the vegetation, so the island was pretty much completely gone. Today we have the unchecked population of humans. If you take a look at that, you will see that the population, even though we have 3 countries where the population is decreasing because people are not having kids, United States is the 3rd one of those 3 that joined. So Japan was the leading one, followed by Germany, followed by US, where the population birth rate is below replacement level. meaning that on average families do not have 2 kids, they have less than 2 kids, so the population is not being replaced at the same. So those are the 3 dying nations currently. Most of the other nations have a positive ratio, or whatever it's called. So now we're going to take a look at the website where we can take a look at the world population and then just calculate exponential model just to see the way this is done. I'm going to go to population clock. Population clock is the government website, so you're looking for population clock Census Bureau, so that's .gov. And if you go to there we go, you have the United States on one side, you have the world population on the other side. You see the way it's the numbers are changing. You also have the top 10 most populous countries in the middle to the right. China number 1. We all know that, right? Because we play PUBG. And then there is India, United States third with 331 million. If you go all the way to 10th place, last year Mexico overtook Japan, because Japan is currently the fastest dying nation in the world, followed by Germany, followed by US. So these are the current numbers. Now, obviously, these are all mathematical models. No one is going every second of a day recounting all of the people on the planet. These are the best mathematical, very complicated mathematical models. So we are going to do something very simple that just approximates these things. So that's the U.S. population, and we can either talk about the U.S. population or we can talk about the world population. But for right now, I'm just going to talk about world population as a title, world population. And I'm going to write this statistic down, that the year 2019 has the population of 7.6 billion. Or we can take 2 decimals, so 7.59 billion. So I'll switch. I just want to go, so you know I'm not cheating. I'm going to type world population in 1980. Doesn't matter, we can do any year. I don't really care. 1980, whatever. World population in 1980, 4.44 billion. So year 1980, population 4.44 billion. I'm just gonna go into 1970 real quick. I just want to see where's the half. 3.6. So that's actually less than a half. How about, do we have a statistic for 75, or it goes every 10 years? 4.0, so maybe about 72, huh? 3.84. There we go. So not even 40 years ago, right? 37 years ago, population on this planet was half of what we have right now. Exponential growth is a very scary thing. We are all used to linear growth. When you're talking about exponential growth, it is very, very tricky, especially if you don't understand mathematics. For that, I have one of my favorite questions, just to test your perception of reality. I'm going to erase this, but I'm going to draw a jar and I put a bacteria on the bottom. Now, bacteria is split in half, right? And then you have 2 bacteria, and then after some time, right, splits and so on. So I'm going to say that it's noon and the bacteria splits every minute. So bacteria splits every minute. And I will say that at midnight, so that's 12 hours later, the jar is full. So let's say that's the way the bacteria splits. So it splits every minute. And so at what time? So you have the noon, you have the midnight. At what time is the half full?
Before midnight.
1 minute before midnight. Yes. So at 11:59 p.m., the jar is half full. Because what happens the next minute, every bacteria in the jar splits in two, and it fills up the second half. So it takes a minute to fill a half of a jar. Welcome to exponential world. And now you say, well, we filled out this jar, this planet. Well, simple. Just move to Mars, right? Because you have a full planet. Okay. Here's the Mars. Here's Mars. At what time is Mars full? 12:01. You see that? Because when this is full at midnight, right? Every bacteria that is already in the jar will split, filling up immediately the second jar. Now, at 12:02, how many jars do I actually have at 12:02 if everything is full? I have 4. And at 12:03, I have 8 jars. Can we find planets at that rate? No, we can't, right? You see that exponential growth in population is not easy to contain when you don't have natural predators, right? And we're constantly getting better with medical, constantly getting better with everything else. So population issues that we see, right? Well, there are the numbers, and the way it goes is we're going to set 1980 as t equals 0. So if 1980 is t equals 0, then 2019 is going to be t equals 39 years later, right? When you subtract. So we are setting 1980 as t equals 0, which immediately means that my population P0 is 4.44. That's my initial population because we are setting up the start of our calculation, right? The start of everything at t equals 0. So if I have the model to be, first of all, let me write this. Y equals AE to the KT. That's the exponential model. But then when you apply it to population, you will say that P as a function of T is going to be P0, which is your A, E to the KT. So we're just going to use, instead of Y and A, we're going to use P for population. Now P0 is initial population. So P of T is equal to 4.44 E to the KT. And now we use 39,7.59. So we use 39, to come up with K. Once we have K, we have the model for population. Now, and then pre-calculus is done. So I have that the P of T is 759 equals to 4.44 E to the K times 39. As you can see, the only variable we have here is K, and we can compute K. So to work this out, we will divide 7.59 by 4.44 to get 1.709 equals to e to the 39k. We ln both sides to kill off the e. So ln of second answer, make sure you keep 4 decimals, 0.5362 is equal to 39k. And now we see that k comes out to be positive, which means population is growing. So this number divided by 39 is 0.01375. Guys, I'm not keeping, sorry, I said that's wrong. I'm not keeping 4 decimals. I'm keeping 4 significant figures. So this number here, I kept 4 decimals because those were significant figures. Over here, these two don't count as significant. So I'm keeping the non-zero 4 decimals as significant, and then whatever amount of zeros I had. Because remember, if your number is 0.0000037 and you're keeping 4 decimals, do you see the issue? 1, 2, 3, 4, and then you just delete the rest, right? So it's not, you're not keeping 4 decimals, you're keeping 4 significant figures, ignoring all the zeros that do not impact your calculation when you start dividing and multiplying and doing all that stuff. Great. So now we have a population as a function of time that is going to be 444 e to the 0.01375 t. This will be known as the population model. And now you can plug in whatever value you want for t, and you can calculate the population. So now you want to say, well, what is the population in 2000? What is the, so you will plug in t equals 20, right? From 80 to 2000 is 20, so t equals 20. Now, the problem that we were interested in was, you probably heard about the talks from scientists about carrying capacity of the planet in terms of population. Carrying capacity is this number that scientists can't make up their mind about, that fluctuates anywhere between 10 to 15 billion. And if we have that many people on the planet cannot sustain the population anymore because there is not enough land to build on and grow food and minerals in the ground, and because the planet is the finite size, we don't live in the water, we don't live very well on Alaska or any of the poles, and we don't live very well in deserts and so on. So I mean, there are people living there, but you know, very, very few in comparison to how many you have in Somerville here, all right? So the carrying capacity of the planet is something that scientists is trying to figure out, which is the use of energy and so on. And given that we don't have fusion figured out and a lot of other things that we actually need to progress as a species. So let's take a look at, so numbers are anywhere from 10, 10.2 to 15.2. Those are all the reports and papers that I've read. So what should we take? You can literally take any of those two numbers or anything in between. What should we take as a number where the planet cannot sustain any more people? Do what? No, I'm asking you to pick a number between 10 and 15. 12. So let's say that the argument is that if population reaches 12 billion, any next person will not be able to get any resources because there will be no more. The planet can only support up to 12 billion people. So if that's the target, we can see by this model, when do we get to reach 12 billion? This is also pre-calc. So when do we reach 12 billion? Because that's a scary number, let's say. Well, you will just plug 12 in here and you will work out the time, And then just remember that whatever number you get, you have to add that number to 1980 because 1980 was our time zero. So you have the same calculation, 12 divided by 4.44, and that gives us 2.7027 equals to E 0.01375t. Hit ln both sides. So we have now ln of the answer on the right hand side. Works out to be 0.9943. And on the right hand side we have 0.01375t. So now we divide this by 0.01375 to come up with t equals to 72.3. When you add that to 1980, you get that the year is 2052. So 2052, which is in 30 years technically, we will, by this model, reach 12 billion as the population. Now, is this sounds okay? Well, of course it sounds okay, because if at 1972 we had half of the population we have today, right, then you can see that in next few years, because remember, exponential functions grow fast. So the further we're going, the faster it's growing. So now we first want to calculate we first want to take a look at how good our model is. And this is something that you will be doing in differential equations a lot. When you have any kind of system, you want to see when that system is set off to work, which is like population or clock or whatever, you want to see what happens if you let it run for infinite time and you achieve that to the limit, which is how we sneak in calculus to these problems. Everything you have seen so far, you were supposed to be able to do like this, because that's a pre-calculus problem you guys learned a year or two ago. Calculus starts now. I want to test what is the limit as I send time to infinity for my population, which is 4.44 e to the 0.01375t. And we quickly see that that is infinity. So we immediately see that on the long run, this model is garbage, because we know that on the planet that it's finite surface area, we cannot fit infinite amount of population of anything. You can't have infinite amount of people, you can't have infinite amount of ants, it doesn't matter what it is, infinite of anything doesn't fit on a finite surface. So we immediately see that this model is not good for long calculations like that, but we can work this model locally. So try not to go more than 50 years back, more than 50 years in the future, because you would have to actually recompute to make your model fit the data better. Now, there are other models like Logistic Model and other ones that would actually take the carrying capacity in consideration. So I'll just put it here on a side. Way to fix this is to use the logistics model. Now, this is something that would actually have a carrying capacity, usually known as K, in it. So you will start with some initial population at time equals 0. Population will grow exponentially, and then it will just level off as it approaches, because it is hard to get the resources at this point, right? The closer you are to the carrying capacity, the resources are becoming scarcer and scarcer, so it's harder to reach them. And this model is much better, and obviously it will mathematically make sense, because when you take the limit of that, you will approach the K, which is the carrying capacity. Now, that K, again, scientists can't figure out, do you want to use the 10 billion, you want to use 12, you want to use 15? So I've read a whole bunch of different papers, and they keep going back and forth because they keep looking at the average consumption, right, which is for Americans much different than Nepal. Most of Nepal lives at $1 a day, right? Over here, you can't get far with $1 a day, right? That Gatorade you're drinking is more than $1, right? Which contains the entire meals and everything for someone from Nepal. So there's that. So this is the first way we sneak the calculus into these exponential models. The next way to sneak it in would be to take the derivative. So we have our population model, which is P of t is equal to 4.44 e to the 0.01375 t. And now we're going to take the derivative P of t. So when you take the derivative, you know that when you take the derivative of exponential function, this number jumps down and multiplies the number you have. So it's going to be 0.01375 times 4.44 e to the 0.01375 t. What do we get when we multiply these two numbers? Anyway, we have the expert over here. Good. Thank you. .61. Okay, 0.061. Thank you. E to the 0.01375 t. So now we have this function. Now, what does this calculate? Well, if you studied Calculus 1 and you know, then you know that derivatives calculate instantaneous change. So we can calculate how many people, as units, how many people were added in a particular year. So let's write it here. Calculates how many people were added in a particular year. So if you're interested in how many people are added, how many people are going to be added to the population this year, right? So you would compute P of 39, right? So you calculate P of 39, and that calculates how many people you're adding in 2019. So now you will have 0.06, get that calculator ready, e to the 0.01. So you have to work out the exponent first, because you are multiplying exponent by 39. Then e to that number. What happened?
You can be a prime on top of p, that's the derivative, right? Of the function.
Oh, yes, thank you. Prime, right here, prime 39. Thank you. 0.104. Is 0.104? There's decimal after 4?
104.
104, good.
Yeah.
So P of 39 is 0.109 or 108. What do you say? 108 or 109?
This one would be like 0.104.
Oh, 104. Thank you. 104. Now, what were our units for population when we started the problem? Billion. That's it. Now, how much is this? It's 104 million. So this year, we are going to add 104 million people across the planet. Right? Even though Japan, Germany, US are losing population, the rest of the world is going to add 104 million people on top of what we had last year. Now you can go and you can put 40, right? That's going to be 2020, and you will calculate how many more, right, are added in that year. So we can calculate the change of population year by year, and you specify which year you want by simply plugging in the year you're interested in since 1980, because we took 1980 to be our base year. Good, right? We got this. What else is left? Integration, exactly. So the third and final way to sneak in calculus in these pre-calculus calculations of exponential models is to integrate between certain years. And that will calculate the accumulation of all people that are between those 2 years. So let's say you want to calculate 37 to 39. So the last two years of 4.44 e to the 0.01375 t dt. Now, when you are integrating, you know that you are dividing by the number that is in the exponent. So we have 4.44 e to the 0.01375 t divided by 0.01375, computed from 37 to 39. So now this is far more annoying calculation, obviously, than anything before, but it will give us a different concept to work with. So let's quickly, so 4.44 divided by 0.01375. This gets us 322.9 times e to the 0.01375 times 39 minus e 0.01375 times 37, because you have to do upper minus the lower. So 322.9, open parenthesis, e raised to 0.01375 times 39 minus e raised to 0.01375 times 37. $14.97 billion. What is that number? What do integrals compute? You'll say area under the curve, but yeah. But yeah, that's all it is. So what this number calculates is all of the people that were alive around in the first year and the second year. Okay? So remember how our population is about 7 billion. Well, that's 14, right? It's times 2, technically. Now, clearly, a lot of those people that were alive in the first are alive in this one as well. Integration calculates accumulation. Now, we don't need to force every calculation every time. Sometimes we have more use, sometimes we have less use. Sometimes for my Calculus 1 project, I assign a rainfall problem where you are supposed to calculate how many inches of rain falls in the particular months. You have a function that models the inches for the full year, and then I say how much rain do we get in the month of October, and then you go, okay, well that's 10 to 11. Sorry, yeah, September is 9, so 9 to 10, then 10 to 11. Good. So you can calculate. No, January is 0 to 1. January is 0 to 1, so this is 9 to 10 for October. If you start 0 to 1, then yes, okay. So you can calculate for 1 month if you just use 2 adjacent numbers. Just think which way it's set up. It depends on which way the model works. It says that. I can't remember. And then also, how much rain did we have in this area for 3 months? Well, the limits are now 3 units long. So you can calculate accumulation. You can calculate the instantaneous increase for 1 year, and then you also use the limit that goes to infinity to see that the model is actually garbage for the long run, because you can't have infinite amount of people, and we all know that for the finite surface area and finite resources, you have to cap it up at some point, which is what other more complicated exponential models are for, and I didn't mention logistic. There are other ones as well. So this is the exponential growth. Now we're going to take a look at exponential decay, which is the second type. Did you guys hear of doormat? Anyone? Doormat? No? Oh, you're in for a treat. Doormat is first ever teeth whitening toothpaste on the market. 1940s in Germany. 1940s. People were concerned with their beauty, and they wanted a very shiny white teeth, so when they smile, they glow. And they achieved it with that toothpaste. That toothpaste contained sizable amount of thorium-229, which is the radioactive isotope of thorium with a half-life of 7,340 years. All of those people died very quickly, needless to say. But they had a pretty smile, right? So I would like to calculate, now that it's been almost 80 years that these people are dead, I would like to calculate the amounts of the thorium that is still on their teeth, because we can do that with these calculations, right? Now, before we do that, we have to talk about the words that I mentioned, which is a Half-Life. Apart from being one of the best video games ever made, are we ever going to see the third one? What do you think? Never. No, they're now business. They don't make games anymore.
Even if they make it amazing, it'll still get backlash. So.
Yeah. I don't know. I read somewhere that we should actually elect Gabe to be the president, because he's not good with making anything number 3, right? So there will definitely be no World War III if he's the president, right? It's Portal 3, not there. Half-Life 3, not there. Right? Team Fortress 3, not there. Like, none of the 3s are there. You have 1 and 2, and that's it. Capped out. All right, so what's Half-Life? Half-life is the time. It is actually denoted as lambda, half-life in math. So half-life is time. Time. Which needs to pass in order for a mass to decay to half of its original value. So if you pop Advil pill, which has biological half-life of 1.9 hours, it will take, call it 2, it will take 2 hours for half of that pill to be gone. All right? So metabolizing drugs in a system. Let's say you take a 500 dose of Advil, which I believe are 2 pills. Each one is 250, I think, or I don't know, but I don't take it, but whatever. So let's say you take 500 milligrams. After 2 hours, there is 250 left, right? Half is metabolized and gone. 250 is still around. Another 2 hours pass. How much is left? 125, right? Because it's half of 250. Now, what do you do after 4 hours? Yeah, you take it again. So now, after 2 hours, because 4 hours has passed, you have 125, and then you take another 500. So now you have 625. Every time you take a next dose, it actually increases the dose of what you had, because the previous stuff didn't metabolize yet completely. Now, if you look at the graph, when does the drug metabolize when you take 500 of anything? When does it metabolize? When is the level 0? Never. Hello, right? Do the screening for everything you ever took. We just don't have good machines to measure it. Everything is still there, mathematically speaking. You see it, right? You know what the decay model is. So now you have 625 after 4 hours. So you started with nothing. You took the first 500. 2 hours went to 250. 2 hours went to 125. You took another 500. Now you have 625. After 2 hours, what happens? 300. 12.5 milligrams. After 2 hours, what happens? 156.25 milligrams. But that's the 4 hours. What do? Boom, plus 500, right? That's the next dose of the, right? The next 2 pills. 4 hours later, I still feel slight discomfort, right? Then you wonder why you bleed from the left eye and the rest of your life. Because they always mess up something else, right? It's like, yeah, I don't have the pain in my left leg now, but I can't stop the bleeding from my eye. So now you are at 625. So when you check at the places when you took the dose, you took it here, you took it here, you took it here. What do you see? The increase in dosage, right? Oh, you get hooked? Really? Why? Well, you don't know math, right? So that's half-life for you, right? Half-life, it's not half. You lose half, and then in the next 2 hours, you lose half of the original amount. You lose 250, and then you lose 250, and you're done. No. 250, and then 250 remains. You lose half of that 250 because the problem resets, right? The half-life means whatever is there, you're waiting half-life for the half of whatever is there. So this is the reason why you never go down to a 0, especially if you are taking new dose and new dose and new dose and new dose. Now, you know, anytime when doctor wants to wean you off of medication, they prescribe smaller doses, right? You take a pill, and it's some terrible pill, obviously, right? And then after a week, you take half of the pill, then the next day you take half of the pill, then the next day you take a quarter of a pill, and the next day a quarter of a pill, right? So they go gradually because you will not be adding this much, so actually it does go down. So all of those have mathematical basis. You have to calculate these things. And I don't know if you ever went to Wolfram Alpha and typed any of the drugs. I was really surprised to see the. So Wolfram Alpha is the free online computing, right, from Mathematica. Now, if you install Mathematica through that link I gave you in the syllabus, you will have the full software on your computer, and you type Advil, let's say. I don't know why I get the Advil, but you got everything. Input, interpretation, ibuprofen, or ibuprofen, whatever it's called. There's a formula if you want to cook it at home. You have the Lewis structures and the molecular structure and, you know, all that good stuff. Molar mass, blah, 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 and boom. Biological half-life, 1.9 hours. Says right here. It says the way it interacts with other drugs and all of this. You can put anything in this thing, it will grind it through this. You can put orange juice. And you get all mathematical facts about orange juice. There's this, and then there is all this mathematics afterwards if you're interested, right? One of my projects for pre-calculus is to work out the mathematics of your breakfast, right? So you get to go and calculate this, and you get to modify your juice because these blue things over here, Capri Sun, 25% less sugar, orange juice, and then you can change it more, and they all different ones with calcium, with this, with that. So you get all of the nutritional values right there. So if you know, you can custom build your breakfast before you go out and buy it. Good. So now that we clear that up, we understand, hopefully we understand half-life. We understand that it's killing half of the mass every time it ticks. The next issue for us is to calculate what is happening with this toothpaste Doramad, because for Doramad, I already pulled the images. These are all the commercials, 1942, 1943, and you also have the toothpaste over there. So these are the images. If you go, this is the real thing, right? So it contained thorium, half-life of thorium-229, 7,340. So Doramad, thorium-229 with a half-life of 7,340 years. Now we understand what half-life means. If you put 1 gram of thorium on a desk, you have to wait 7,340 years for that 1 gram to go down to a half a gram. If you put 1 pound, you wait 7,340 to go to a half a pound. Now, generally, radioactive elements don't like to have a lot of mass. Not sure if you know that you're not supposed to make 1 pound ball of plutonium at any point because it immediately detonates itself, just if you put it on a pile. Look it up. These things are not a joke. That's why there are heavy regulations on all of this stuff. And you can't really make a home lab to make it because it's very complicated and very dangerous. Most likely you'll die before you make anything significant. Well, yeah, but that's a fusion one, so that's not an issue. I worked on the same thing with my students. fusion reactors are not the same as fission reactors. Fission reactors and nuclear bombs work on the same. Fusion is the implosion. So there is literally nothing wrong can go unless you're standing next to it and you get significant amounts of X radiation. X radiation is dying with the square of the distance. So generally for the size of the device he had, if you stay about 6 feet away from it, you would get the same amount of radiation as when you are taking the X-ray at the hospital. Now, obviously, if you stand right next to it as it's on, you will get significant amounts of radiation, which is again, it's bad, but it's far better than what the fission is, because fission, you have the uncontrollable splitting, which releases energy, and it's still only 5% efficient, which is terrible efficiency, but it gives so much energy that we don't care. It's still the safest one we have, but it creates nuclear waste, which is a problem. Fusion has no waste. It produces heliums for balloon, so woohoo, party. Anyway, back to Doramed, back to thorium-229 with its half-life of. So now I want to calculate. Remember, our model is y equals a e to the kt. Now I'm using it as a mass. So I have mass at any time t is the initial mass times e to the kt. And what we know is that the mass will be half of initial mass when time is equal to half-life. So this is important aspect to know. Your mass will be half of original mass, right? Remember, you took 500 milligram dose, you waited half-life, now it's half of that, it's 250. So I get to write m over 2 is equal to m e to the 7340 k. M's cancel, and I get 1/2 is equal to leave space e 7340 k. Hit both sides with ln, and we calculate k from here. So ln of 1/2 is negative 0.6931 equal to 7340k, and we see that k is negative. Well, obviously it's going to be negative, it's a decay model. So the number we have divided by 7340, that will give us 0.123 zeros 9443. And here it is, my model for decay of thorium in time. So you have initial mass e to the negative 0.0000943 t. So that's my model. And now, if I know how much thorium, you can go and research how much thorium in grams or whatever was in this toothpaste, how much thorium you do get to put on the teeth when you brush once. Well, hopefully you won't brush, but I don't know, maybe you like to glow. Because you can, make a pretty Instagram picture with it. Right? Yes? No? Right. So you have this. Now what I want to know now how much thorium is left after 80 years. These people were dead 75 years, let's say, but let's round to 80, right? So what percent of thorium-229 is left after 80 years? 80 years will be in, about 3-4 years from now, but call it that. Okay, so unknown percent P, yes? No, why?
Like, I just used the one of the initial final is equal to the original initial amount after that the power of amount of time it takes divided by
Yeah, but it's just extra formula. Sure. An extra formula. You can use it if you know it, but it's just extra formula for extra headache for no reason. But if you like it, sure. Yeah. All right, so what do I have? Well, I'm looking for the percent of the mass of thorium that is left. So that's the percent of original mass that it's left in this model. And I know that my time is 80 years later. Now, percent, I'm not going to put the percent symbol, I'm just going to put little p, because that will be percent times m, right? Percent times m. Now, m's cancel again. And we just get that the lowercase p, which stands for percent, is equal to, and now we calculate this number. So, E raised to the open parentheses, second answer, times 80, close the parenthesis, I get P equals 0.99247, blah, blah, blah. What's the percent that it's left? 99.2% left. These people are dead for 80 years. The deposits of thorium on their teeth are 99.2%. See that? So, yeah, don't mess with thorium. Now, other isotopes have longer half-life. Depending on which isotope of thorium we talk about, I saw another isotope of thorium-230 with a half-life of 75,000 years. Yeah, talk about that one. 10 times worse than this. But anyway. So this section was all about computing these things. Now, can I take the derivative of this model? Sure. I'm going to calculate that minuscule percent of thorium that it's lost in any particular to decay in any of the particular years. So let's say, all right, how much was lost in a year 10 years later after their death, right? So you put 10 as the exponent t once you take the derivative, and you will come up with a number that will represent that little smidgen, insignificant smidgen of thorium gone within that 1 year, because remember, your derivatives compute the change inside 1 year. And if you want to calculate the accumulation of thorium, you will integrate. It's all of these concepts that you guys learned in calculus you can now apply to exponential models, and you can compute a lot of these interesting things, right? See you tomorrow. Bye.